Hello YouTube and welcome to my presentation on research questions in applying quantum computing to systems design. This was presented at the International Conference on Design Computing and Cognition in 2022, and we have the paper in the description below, so if you want to go and read a bit more about this, then yeah, please feel free to click on the link. There we go. So just a little bit of overview of systems design. As it is like it's a common concept of the idea of we have a set of parameters, maybe it is a set of combinations of gears and shafts, or a set of lengths and sizes that we can design products to and for, and that ultimately represents a design space. So we can vary those parameters and create a parametric design or a model that would then create a potential design. Yet then we need to then check that design against a series of constraints. Here we'd say it's like an f of x. Sometimes it's just simple Boolean checks whether things clash or overlap. Others are then simulations that then run some computational simulations, such as here for the gearbox, to make sure we get the right gear ratio and get the right power and torque power coming out of that gearbox. So that takes us to this kind of idea of an objective space, what we want to try and achieve from that design. And sometimes we'll shoot over and hit onto an answer that is plausible, but yet maybe not be optimum. Sometimes we'll shift over to the objective space and find out nope, it invalidates one, two, maybe more constraints, or just does not perform optimally for the case. It doesn't give us the performance we want. So the idea is that, the challenge for us as designers is to have computational methods that can go iteratively explore those design spaces. And in this example here, they might be discontinuous. So it can be hard to know that actually there is another solution, but it is like a leap away, which is typically challenging for gradient descent type methods. So it is, depending on the complexity of the challenge, quite complex to find out when you've got large design space where you sit in it and where the optimum lies. So I just want to give you a number then, just about like how big these design spaces can be, and I'll give you the number 5.18 times 10 to the 18, and that is the number of options for a three-stage gearbox. I mean, we're just thinking 3 stages of motors, of shafts and gears, and a motor system where we have 17 gear options for the 6 gears. We have 5 materials for those shafts, 9 bearing options for the 8 bearings, and 8 electric motors for the motor to choose from. So a huge already number of potential options and combinations that we might want to evaluate. And then I'll give you another number, which is 164 years. Now, this is the time that it would take to compute all of those options on a simple 1 gigahertz processor, if each option could be evaluated in 1 clock cycle. So there's a few assumptions there, but just to give you a flavour, if you really wanted to be, complete in your exploration, that is how long it would take. Okay, and that just highlights that we are unable to evaluate all options for our systems design problems. And I'm sure you're probably thinking, well, yeah, but we have, gearboxes today, and we do make them today. And that is definitely the case. That's why, as mentioned before, we have these kind of gradient descent methods, we have evolutionary methods, swarm, linear program, constraint-based satisfaction. All of those algorithms are built to try and navigate those design spaces efficiently, so we don't have to evaluate all of the options. But they can be troubled by local maxima and minima, so they might fall into a well here. This is a kind of like illustration of where you might go, there's an optimum, but you may be on this right optimum on the graph, but actually there's a much better optimum much further along. But of course you've fell into that local space of, this must be the optimal result, but I didn't realize it's much further along in the design space. We have disjoint design spaces, so that illustration before, where I actually might have pockets where actually in between them there just are solutions that just do not satisfy our requirements, but much further abroad there are these islands of potential solutions. And again, if there's that barrier when you're doing some kind of algorithmic approach where you're trying to navigate you might hit upon one of these, let's say, so-called walls, where you just don't know that you could go much further beyond it, kind of almost leap into another zone. And how does a algorithm, predict or even anticipate that? And yeah, then we're limited by classical computational time resource. So we can only run for so long because we want the answers. We want to be able to go and get onto the next stage of the design process. So fundamentally, that brings us to a point where, well, because we can't fully evaluate that design space, we'll always have that question mark over the answer that we get from those algorithms, and there's always an uncertainty, and it requires expert designers and engineers to have their judgment on whether that solution is suitably optimal or is the right solution to go forward. So we still have that human in the loop, expert opinion, making those decisions for us. So across the road from us is the Quantum Computing Research Centre in Bristol, and we've started doing some collaborations with understanding the potential for quantum computing as a means to solve some of these systems design problems. So a quick brief, like you say, maybe rudimentary understanding of the difference between classical and quantum computing. You can imagine quantum classically is about iterating through options, evaluating each one. You can parallelize that and do that multiple times over, but fundamentally you're iterating through those options. In this quantum space, quantums are represented by qubits, and it's that it's the quantum version of a classical bit. But in that, we can set them into superposition. And the idea, or the premise that we're playing with, is that we set them into superposition to represent all the design options in one instance. So in one instance in time, they are all existing. And then we apply our constraints and models to that problem. And then we sense that state. That then takes it out of the quantum realm and it returns an answer. And if we set up constraints right, it will discount the wrong answers and will give us a valid answer to our problem. And there are numerous number of algorithms that have been created over the past 20, 30 years. And we're now in a mode of exploring which ones are suitable for our types of engineering design problem. And the one that we've been focusing on here is this idea of Grover's algorithm. So that's it. So we're kind of taking that quantum computing toolbox and looking to say, well, how hard can it be? How can we apply it to a systems design problem? What are the challenges in there in doing so? So given at the moment the state of quantum computing, the computers are still in development. They're not as robust as our classical counterparts. We still got to use quite simple problems to actually be able to compute them on these machines. So we've just a 2D tiling problem where you can't have the two tiles overlap, and it's in an 8x8 room. We've got the two tiles there. Yep, and they want to be on that east wall in this road, and we can't have them overlap. So we just wanted some simple constraints and said, yeah, how would we go about setting up that problem? One aspect we did look at is looking at the dimensions there. Of course, we've set them into like a binary set of dimensions there to represent different spaces. And that one, this problem gives us 4096 design options when you evaluate it all. And once we've done it classically, we know there's 56 valid options in that given those constraints. So that's what we were looking for. So just checking whether we've set it up correctly. So yeah, out of the toolbox, we pulled out Grover's algorithm with the anticipation that it will give us a performance benefit of up to square root n, rather than n over 2 for undirected search, n being the number of operations that you need to do. And Grover's algorithm can be broken down into 4 steps. We want to do a state preparation, so that's where we want to get our qubits in a state where it can represent every single design option. We do that typically by setting them into superposition. We then look to apply the oracle, and that contains the tests to determine whether that's each out of all the ones that are in all the solutions that are existing, which ones are valid to our problem. And then the ones that are valid receive what they say by doing these set of rules. The ones that are valid will receive a phase change by interacting with a qubit that's out of phase. That shifts it, so we then get a set of qubits that are in phase and out of phase based on whether they are valid to our problem. Then we use the diffuser, which is effectively like this kind of geometric reflection. It's in the bottom right there, to promote the valid answers above the invalid. And we need to repeat this step, typically square root n times, to promote them in such a high probability when we collapse this quantum space, we receive a valid answer. So that's where we do repeat square root n times and measure. So that's what we did. So this is our quantum circuit that we built. This is using Qiskit. We'll use that to run the simulation. We'll quickly run through it. Just to say, so these are the qubits at the top there representing one tile. This set of qubits are representing the second tile. And these like clause bits are qubits that were used for helping to determine whether the scenario is setting up, it's a valid scenario is set up against our constraints, valid against our constraints. And then the V1 there, again, that's already set into a phase change. So we'll then, of the valid ones that are detected, we'll set that phase to the valid bits. So first thing we do is set all those qubits into superposition. So now we're in a state where all our options are represented in this quantum space. We then look to apply the check for the representing on the east wall. So this is saying, yeah, we've got to be on the east wall. It's just checking whether all the x points are, making sure the x coordinates is on that east wall. And if true, it will flip those clause bits. We will then look at applying the clause, the constraint. This is for no overlap. So it's checking each of the respective positions for each of the cells and saying, okay, are the tiles overlapping? And if so, again, we'll if not, they'll flip a bit. Flip a bit, the clauses will activate. And then we'll go, right, if we're both not overlapping and we're on east wall, well, then they'll receive the phase change. We then need to repeat that step just to bring the state of all of those qubits, because they're in entanglement now. We need to bring that back to the original state where we hadn't applied them before. So it's back to as if they were their original options. And then we apply the diffuser, which then increases the probability of the accepted ones, the ones that pass the test, there'll be more chance of being reported back. And what we ended up, which is great, we were successful in doing that. So yeah, we reported back the same tiles, some with higher probabilities than others, and it showed that in essence, yep, we can start building out these problems and using quantum computing to solve some kind of typical systems design tiling type problems. But what did we learn by just going through that process? And that's really what we reported in this conference paper. Well, how we map and index the set of design options. There were some simple indices there because it was just x and y, but you could imagine more complex system design problems having sets of parameters that are a bit more complex to set up in a form of qubits, which would then represent the right range of design options. Are there some standard building blocks for building out the system design problems in a quantum computer? Can we get to a stage where we've got like a systems design toolbox? So like you say, setting these kinds of no overlap, no on this wall or not in this location. Can we start creating a toolbox of situations that then people can click and drag effectively and build out these problems that a quantum computer can solve? What are the actual quantum compute requirements to solve typical constraints and the performance criteria, whether one is better than the other as well? We need to move to that stage because we've just said they're valid, but you could say there's also means that we want to assess their performance in some sort of like linear or non-linear metric. And yeah, what sets of constraints are really achievable in the kind of what we're in at the moment, this NISQ era. So on a real quantum computer, there's a lot of noise generated, so we do get erroneous results coming back. But can we still can it still function suitably to get us results that we need? And is there maybe a systematic method of removing known solutions from a valid solution set once it's run? So because typically there might be multiple solutions that are valid. Once we've got that solution out of this computer, can we then set the constraints up to ignore that one? So then further promoting the ones that we haven't observed yet. And then there's the idea of this kind of hybrid computation. So maybe using a quantum computer to do the early stage, you maybe like say Boolean type checks on a vast space. If you imagine right back to that first slide where we've got these kind of islands of solutions, can we use it as a spotter to identify the islands, which then we can then have the classical computer then like going to zoom in and focus on. So it helps navigate the classical computing algorithms and set them up appropriately to identify the optimum solutions. And yeah, at the moment we're looking at constraint satisfaction, Boolean, true or false, but how do we move to more of a scoring method as well? How do we score in a quantum realm? And then I think it's maybe it's one more. Is how can quantum algorithms support how can other quantum algorithms support systems design? We've only taken Grover's at the moment, but yeah, we're going to further unpack and understand how we could use and apply the others in this context. And there are other aspects of can we speed up the checking algorithms? We've got them working, but we never know if they're like the optimal way of checking constraints in that space. There may be other ways of performing the same checks with less gates, and we can then reduce the size of the circuit, make it more probable that we could deploy it and run it on real machines today. So with that, thank you very much for listening. The links are on this page, and yeah, looking forward to connecting up, scan for more information. Again, the link for the papers in the slides. So I hope to see you soon. Thank you very much.